be chaired by me, Marcelo Farenzena, and Bruno dos Santos from PUC-Rio. The first, we're going to have the presentation of Professor Jorge Trierweiler from Federal University of Grande do Sul, and he will present the work entitled Assessment, Diagnosis, and Maintenance of Industrial MPCs in the Digital Transformation Age.
Thank you very much. It's a pleasure to be here. And what I will share with you is the result of our research. This research started in 2002 in collaboration with Petrobras. In that time, Petrobras started a collaboration with us, with Professor Gemiro. Do you prefer there? All right. And then we start this collaboration related to assessment, diagnosis, and maintenance. And what we will see here in this presentation, we will see how we solve this problem. And it's a very complex problem because we are working with industrial MPC. The first thing that we learn is how is an industrial MPC and how is the difference between an industrial MPC related to the academic world. Then it's the first thing that we will consider. After that, we will then see how can we consider all these aspects here and how we have solved it in an industrial perspective that combine industrial point of view with basic theoretical theorems. Then let us start. Here is the overview of my presentation. Here we can see all the slides, and I will speed up the end because I will have no time to cover everything. But I will start with the first thing. The first thing is related to the problem. And it's very important to know that it's a very challenging problem. Because why it's a very challenging problem? Because it depends on the model, and all models we have model-plant mismatch. Then we need to quantify this model-plant mismatch and how this model-plant mismatch affect our result. And another very important issue related to this topic is that it's common to have unmeasurement disturbance. The unmeasurement disturbance is another very important issue. And another point that is very interesting and important is tuning parameters, because we have different implementations of industrial MPCs. For instance, when we think about Petrobras, in Petrobras we have 3 different model predictive controllers. And then we are looking for a methodology which is able to work with all these different model predictive controllers and solve the problem without to specify in details a particular MPC controller. But let's go further. The first thing that we have learned when we start to work with Petrobras is that the academic world, we usually have square systems. And in the Petrobras and the industrial MPC, usually we have more controlled variables than manipulate variables. The system is rectangular. And this makes a big difference because we should not work with set points, with square systems. We need to work with multivariable system, which is time variant. And usually this time variant system is quite difficult because we need to consider the different scenarios, as we will see. And then here we can see the academic world, where we are oriented in the set point, in comparison to the industrial world, where we have soft constraints. And here I introduce you the first concept. Usually when we work with industrial controllers, we should not just think about set points. Yes, we have set points, but we have what we call variables controlled by range. In this case, we call it fat points. In fact, we have a large area where the variable is inside. When the variable is inside, it's like to have a set point satisfaction. And sometimes this is small, but be large also. And then it's a quite different point related to industrial perspective. And how can we consider this? And another very important issue is related to, usually when we work with industrial MPCs, we have an economic layer. This economic layer usually change the set points, the targets, the fat points to the MPC. And then we have always a system that is changing the operation conditions. And changing the scenarios, it means changing which are the squared part, which is really active. And it's very good on the side of model maintenance. It's a very good issue, because I will show you that based on these perturbations, we are able to identify which kind of problem we have. Let's go further then. Then our wish list at the beginning of our research was this one. We should have a system or a procedure that consider exactly the frequency range where our controller works. And then we should then quantify this model plant mismatch exactly in this feedback, considering this feedback effect. And I will show you that we have done it quite well considering our approach. And then we define, to capture these two things here, we define what we call Y0. Y0 is our reference, our performance reference. And this performance reference can consider this. And then we need then to work with industrial MPCs. As I already mentioned, Petrobras, we have 3 different implementations, and then we should then work with all of them. And then we then need to decide if we are having model plant mismatch or unmeasurement disturbance. And then after we identify if the problem is related to model or to disturbance, we need to show or identify which channel we have the problem. Because if you know which channel we have a problem, we can then identify this channel, what can reduce considerably the time to maintain and to update the model. And then after that, we identify the model, and then with a new model we can tune. Then we have developed, together with Petrobras, a complete methodology which is able to consider all these points. And I will show you here for you. The first things we need to work when we work with multivariable systems like more CVs than MVs, we need to work with active scenarios. And then we consider more than one scenario, more than one single multivariable system. And then we consider all of them. And here, then we can go further and to show you what is the base of our methodology. The base of our methodology, we have developed this theorem here. And what this theorem gives us? Allow us to calculate Y0. Y0 is the output in the case where we would not have any kind of model plant mismatch and no disturbance. And then it is our reference. And this reference we use the sensitivity of closed loop, and I will show you closely. And for developing this theorem, we consider here an uncertainty model, and we have a model of the MPC called G0. And based on G0, we calculate the sensitivity matrix, and based on it, we are able to calculate Y0. Let us understand better this Y0 and what it means. Here it's more easy to understand. Here we have two models. G0 is the nominal one, and the magenta line corresponds to the real plant. It's subject to a given input, and when we consider the error, the prediction error of this model, we have this figure here. But the main point is that I can have a big difference between the models, but the models can work quite well in closed loop. And then we need to convert the open loop residue, the open loop error, in a closed loop error. And for that, we use the sensitivity function. In other words, this kind of theorem you can use for any translation of an open loop model and an open loop error to a closed loop error. Because one very important issue is that in closed loop, the error change, the impact of the error change. And what changed this impact is the sensitivity function. And then here we can analyze this graphic here. And then it's the main idea of this theorem. And based on it, I will show you that we are able to develop several different points that solve all the problems that I have shown you before. Then another very important point you can ask me about, how can I get this T0, this closed loop response or the sensitivity closed loop response? For that, we use a simulation of the real MPC controller using the model used in the control. And then we identify, and it's very simple to identify this S0 for each scenario that we can find in a real plant. In other words, we are able to convert any kind of MPC controller, and we can apply this methodology to any kind of predictive controller. And another very important issue is that a quite related topic is the unmeasurement disturbance. The unmeasurement disturbance is also captured by this methodology, as we can see later on. And here we see how can we quantify if the model is okay, if the system is working well, or if it's giving a poor result. And a very simple way to do that is using the relative variance index, IVAR. The IVAR is the variance of actual variance and our reference variance. If it's close to 1, it means that the system is doing what I expect that they should do. If it's higher than 1, it means that the model plant mismatch or unmeasurement disturbance increase the output variance. It means that we have problem related to this controller. And then if we have a less value than 1, it means that we have a model plant mismatch, but in this case, this model plant mismatch can help the system to give a better performance than the original one. And another way to see also this kind of results is using the autocorrelation function. And here we can then also analyze other behaviors like oscillatory behaviors and so on. Then we have two approaches to quantify how good is the system related to this topic. And it's a very interesting thing because it can apply in different systems with different controllers in different scenarios. Then let's go further. Here the main idea of how we calculate this. We start with process data. We need the set points and the measurement values. And from the MPC controller, we have the control action, which is calculated by the MPC controller. We need to know the nominal model, the model used in MPC. And based on simulation, we can then identify the S0. For instance, by Petrobras, we use the BR Lumina to simulate the controllers they have used at the industry. And then we automatize this, and then we obtain the sensitivity or the complementary sensitivity function. Based on the manipulated variables and the model, we do an open loop simulation, and then based on our theorem, we quantify the Y0, which is our reference. And then we can then calculate the I-var and compare the results as I show you before. Then it's a simple technology which can work with different controllers. And here I show you in a simple example how can it works. Here we have M1 is the model used in MPC, the nominal model. And the real plant are two different real plants. M2 is this one, the green one, and M3 is the red one. And then we have tuned two different controllers. One is faster. The sensitivity, closed loop sensitivity function of this is this one, and the other one is lower. As we can expect it, if I work with a slow controller with model M2, the difference between results that we get with M2 and M1 is almost nothing. But if we speed up the controller, we can see the difference between them. And our methodology consider this and take this into account. And for the model M3, if we do a faster tuning, we can then have a good results, a much better results. And here we can see that the results are more similar if we use a faster controller with M3. And the result of the methodology show us exactly this. In other words, the methodology can consider the performance of closed loop. The closed loop performance is considered correctly in the quantification of model performance and model plant mismatch. Then let us speed up a little our presentation. We have also applied for a multivariable case, and of course the results are similar, and these results are presented in this paper which we have published in 2015. And then let's go to the other topics that I have mentioned. I know now that our model or our system is working well or not. If it's not working well, I want to know where is the problem and what kind of problem I have in our system. And then for that, we need to go to other steps. And then we have here a case. We can see clearly that the results or the performance is very bad. But the problem is we can have a model plant mismatch in one channel. But if we have a system which is strongly interacted to each other, if we have a strong interaction, we then should consider where is the location. And for that, instead to use a full version, which gives us this kind of results, we use a diagonal one, just the diagonal elements of sensitivity matrix or the complementary sensitivity matrix. And these give us which channel we have the problem. Where is the problem? The problem in this case is related to this channel. This result is also published, and based on this result, we can then apply I-var for the general system and for the diagonal one. And here we clearly can locate which is the output related to the problem. Where is located, which output is is strong affected by model plant mismatch or disturbance. And this was published in 2016. And now we need to decide if we have a model plant mismatch or unmeasurement disturbance. For there, we use some correlations. Here we have the two different systems. One is related to model plant mismatch, and another is working not well because we have here unmeasurement disturbance. And based on the skewness and curves, we are able to quantify if we have a problem related to disturbance or to model plant mismatch. If we have model plant mismatch, we have this kind of behavior here. We have a strong correlation between Y0 and E0. And in the case where the unmeasurement disturbance occurs, we have then no correlation like this. And this was then published in 2016 in this paper here. And now we need to know, we know which output is more affected by model plant mismatch or unmeasurement disturbance. Now we need to know which are the manipulated variable related to it. And this is our next step. Here then, we will then develop this kind of index, which is called normalized model discrepancy index. And this one, we do the following one. Here we have the error, the input, and then the model. Based on only, we calculate the partial output. It means the output which is produced only by one variable each time. And then we filter it using the sensitivity function. And then we have a filtered partial output for each manipulated variable. And now we correlate E0 with this filtered version. And then with a cross correlation, we are able then to identify which is the manipulated variable responsible for the model plant mismatch. Now we know exactly where is the model problem and if the problem is related to the model. And then the next step is model update. Before we do that, we have applied this in a delayed cooked unit. This is a real system. It was a plant in Refap. There we have 12 CVs and 7 MPs and 2 disturbances. And just to summarize, to apply this methodology to this system, we found that channel CV11 is where we have a problem related to the model. And here, based on Courtois, we see that the problem here in this variable is because we have a model problem. And then we identified a new model. And after this identification of this model, the result what we got is this one. And now the problem is only related to unmeasurement disturbance. And it was applied in a real system, and it was published in 2019, this year, in collaboration with Petrobras. Now, I have not too much time, but I will show you very fast how can we model update. The model update, we have also developed a new procedure. This procedure uses the same data used by the diagnosis, the same data that we use to identify if we have a problem. In other words, we don't need to perturbate additionally the plant. The data that we have are enough. And then we have a procedure based on it. And here we have developed a new closed loop identification using this approach. And this gives us very good results. It will be published soon. And finally, after I have a good model, I can then update the tuning. And how can we do tuning on this system? The tuning is based also in different scenarios. And here is something that you can also apply in different types of controllers, different controller types. Not just in MPC, you can use it also for a multivariable PID controller or something like that. The first thing, we need to decide which scenarios we want to work, or we need to work, and based on an optimization problem, we calculate the attainable performance. The attainable performance for all these scenarios. And when we know what we can achieve with the closed loop system, the best performance that we can achieve, respecting the manipulated variables and robustness and attainable performance like this problem, we have a reference model. And this reference model then we can apply in another optimization problem, where this optimization problem we can then tune any kind of industrial MPC. And this optimization problem is almost convex. It makes the life much easier when we have a real attainable performance. And then this last stage here is a standard optimization using the desired performance or the attainable performance, considering the model predictive controller that we intend to apply in a real plant. So, and this tuning procedure we have then published in 2 different papers. And now Franzen is already there and want that I finish my presentation, and then I just to complete my presentation, I will show you what we have implemented in a real environment. This system is called Asset Management Platform, is Plataforma de Gestão de Ativos, PGA. It was developed by, together with Petrobras 3 Solutions, and is currently tested in Petrobras. We received already an award by ANP. And in this system, then, the idea is to produce or quantify predictive maintenance, flexible and other things. But related to the topic that we want, we have developed a BR toolkit called MPC-ADM. The MPC-ADM apply this kind of methodology that I shortly present to you. And we have also developed a nice interface where we can locate and have a previous diagnose problem of the system. And then we have also other graphics in this system. And then based on it, we are able then to apply the methodology that we have developed. Then to conclude my talk, after a long time, we start more or less in 2002, we finally complete our wish list. And now we have, or we are prepared to go to the next step. So I would like to thank you very much for your attention. I would like also to thanks to my collaborators. It was a work related to different PhD works, master degree works, and so on. And thank you very much. And I am here open to any question that you may have.
Thank you, Jorge. I think you have time for one or two questions.
Thank you, Jorge, by this overview of all this stage of development for the MPC application in industry. And I wonder if what you have in mind to extend all these ideas for you to put instead of an MPC and nonlinear MPC, how you extend all this?
In principle, for nonlinear MPC, it's more or less straightforward, because you can simulate a nonlinear model, and then you can at least simulate the closed-loop sensitivity function. And one very important issue is that the closed-loop sensitivity function, in another paper that we are publishing, we have analyzed how exact, how should be precise the sensitivity function. And then we can have an error of 20%, and then results are similar. And then you can then use a sensitivity function based on linear model, or identification of linear model, because the sensitivity function is just used for filtering, to penalize the frequency which are most important for the control, and it works also for nonlinear controller as well. And the modeling is similar, because then you can use a nonlinear model and simulate this nonlinear model. And then, in other words, it's quite easy to apply the same methodology for a nonlinear model predictive controller.
Let's thank the presenter again.
Thank you very much. And if you have any question related on it, please contact me. It will be a pleasure to show you more details.
Thank you. And now I would like to invite Mauricio Bezerra from UFRGS to present a nonlinear model predictive control under unsettling. Okay.
So, boa tarde, good afternoon. I am Mauricio. I am professor here at UFRJ. I am with the Department of Chemical Engineering. And as you see here, the authors are from UFRJ, Otávio, Maurício, and Ajimiro. And we have also the collaboration of NTNU. So we have Professor Sigurd Skogestad and Dinesh Krishnamurthy. This work is about subsea processing. By subsea processing, we are referring to treatments that we apply to fluids at the seabed or below the seabed. And the objective is to raise the recovery factor of the reservoir. So you can use, for example, gas compression, which is the subject of this work, with that purpose. And then you will have many benefits, like you can accelerate production during field lifespan, so you can apply to mature brown fields. You can also use for marginal, smaller fields, and fields that are difficult extraction, and also increase the flow assurance. So these are benefits of using this subsea processing. However, we have some difficulties related to these processes. For example, they are becoming complex to attend all these benefits. And as they are located under the sea, they are difficult to access. They are far from coast also. And the fact that they are difficult to access make the maintenance difficult and very expensive. So it would be nice if those processes would be able to self-regulate. And also the controllers should be able to make smart decisions. Well, we are exploring nonlinear model predictive controllers for controlling these processes. So nonlinear model predictive controllers, which is very related to the previous presentation, the nonlinear version, we use mathematical models that are nonlinear. We will also consider operational constraints and try to find optimal control solutions. Besides those difficulties that I mentioned, there are some challenges that we have to deal with. Because the environment under the sea is very harsh, the conditions of, name it, mad oceans are very difficult to work with it. So we have a lot of uncertainties of different kinds. For example, we have unknown disturbances. The parameters were estimated based on scarce data. We have structural uncertainty due to the fact that we use simplified models. And the sensors may be noisy, or we may have lack of sensors. So we have to proceed optimization under uncertainty. Well, we'll treat one specific case. This is a subsea gas compression named Åsgard. It's in Norway, in the continental shelf of Norway. It was the first subsea compression system implemented about 4 years ago. And it is for a brownfield. So the production was declining. The depth was around 300 meters. And the tieback was 50 kilometers. And they decided to implement this under the sea because they had lack of space on the top side. However, the structure was based on top side. So the structure considered a compressor, a dry gas compressor, so we had to have a scrubber before. It is interesting that they built this system like Lego models. They are very large and very heavy models, and they had to mount them as those Lego models. But they were very much, when I say they, it was a real implementation by Statoil. So they were very much concerned about reliability and safety. And so, for example, they had anti-surge control. You have here the anti-surge valve. So this is the case that we are going to study. We are concerned with the surge phenomena. We have these typical curves of pressure ratio versus volumetric flow. We have regions where we have surge, which causes instability, even the breakage of the compressor. So we must work away from that zone, but not very far, because the efficiency is higher near here. So we include a surge avoidance line and an indicator, which is a ratio between the flow in the surge line and in the entrance of the compressor, and we establish a hard constraint for this indicator. So the objective is to study the closed loop for this process of subsea compression, avoiding surge in the presence of uncertainties. The first thing that we had to do was to develop a model, a phenomenological model. You see here the components. In order to make it more easy to identify, we have put in green the equipments where we are manipulating the variables, which are the heat removed, the opening of the valves. We have 2 trains here, and also the rotation in the compressor. And the dynamic states that we are evaluating are pressure and temperature in the scrubbers and in the header. So that was implemented using EDAS, and we will see that the optimization problem was solved using Casadi. So the closed loop objective, we had in fact many objectives that we listed in priority here. The first object that was a hard constraint was to avoid surge. Then we had soft constraints that were in the scrubber temperature and had a pressure. The anti-surge valve should work closed during normal operation. We wanted to follow set point for the scrubber pressure and temperature, and also changes in compressor or rotation should be penalized. So this is the objective function here subjected to the constraints. We developed the terms of this finite cost function so that all these considerations would be taken into account. But we had also two other conditions here. We could use a nominal approach in which the model of the process would be known and the disturbances, but that would be very unrealistic. And if we closed the loop in the presence of uncertainties, there would be problems like constraint violation or bad performance. So we used a robust approach, named multi-stage approach, in which we calculated a feasible solution for all realizations of the uncertainties. So we considered that explicitly in the solution of the problem. The approach that we used was this one by Lucia, in which we consider a scenario tree, in which we consider different realizations of the uncertainty that is discretized. Here, for example, we have 3 realizations, and for prediction of the horizon equal to 3, we have 27 scenarios that would be possible. So we would obtain a solution considering all these different scenarios. Of course, that if the number of predictions grow, the problem may become intractable. So we considered a robust horizon that after this, for example, here, we could keep the uncertainty constant. That would reduce the number of scenarios. If we kept it constant here, instead of 27, we would have here 9. That would make the problem easier to solve. So I will show some simulations that we performed. Here we have the NMPC and the compression system. Here we have the control actions were implemented with the sampling time, this prediction horizon. The robust horizon for this case was considered 1. It was to simplify. The uncertainty, we considered that the pressure, the input of the second train could vary between these 3 values. We had an expected value in a standard deviation. So the model of the multi-stage considered these 3 realizations. And then we made a simulation in which the variable, the disturbance variable, varied like this. Well, I will only show some results here because I had to, due to the time, I had to select some of them. For example, I will not show the first train and other tests that we made, for example, like set point tracking. I will show only the results for that disturbance. And if you see the first line here, we have the output variables, and the second line, you have the manipulated variables. If you see the green line, sorry, the blue line is the nominal controller, and the red one is the multi-stage controller. You have here the pressure and the temperature in the scrubber that we wanted to follow the set point. That did not happen. Both controllers violated the soft constraints. But what is more dangerous is that the nominal controller did violate the hard constraint. And if we look at the manipulated variables, we see that this happened because it was not able to open the valve as the multi-stage one did. Because the multi-stage was equipped, let's say like that, with consideration of different realizations of the uncertainty. So also here you can see that the blue one produced more gas. Then I can move to the conclusions. When we do this study of uncertainty in the subsea processing, by using an unknown disturbance, we see that the nominal one, which is based on nominal conditions, may go, even though it produces higher, and even though both strategies violate the soft constraints, the nominal one violates the hard constraint. And that would be, you should avoid at all under the sea conditions like that that could be really unsafe. So you should consider the problem of uncertainty. So the final message is this phrase that I chose from Eika Solution. Eika Solution was the company that helped Equinor to install these equipments. An engineer there said, uncertainty needs to be taken seriously in all the project for the process to be operated. So that's the main message that I would also like to pass. Here you have my address, and thank you for your attention.
Thank you, Mauricio. Questions? No one?
I will try to make in English. Have you tried another approach to the uncertainty, like kind of Monte Carlo or Latin cube, something like this? Because yes. In your case, the possibilities explodes. Because it's 3 to n,
yes.
where n yes. is the time step, the number of time steps.
Yes, what I think that is important is that this is really a first implementation, because you see, when we considered that these 3 different conditions had the same probability of happening, you see, and only with this assumption, the problem became very expensive in terms of computational costs. So what I think we should do in the future is to have a better description of the probability of these uncertainties, to use a distribution that we may know beforehand, in order to establish the ways they should vary. So, but what we did, for example, for this implementation, the calculations took a long time that the CPU demanded was even higher than the 1 second that we had for the sampling time. You see, so this is kind of still very demanding for some kind of applications. And so I think the consideration of how these trees are designed should be very much taken into account with care. You see, if we know the distribution, okay, we can suppose different realizations, but at the same time, we may have a high computational demand to calculate all the possible solutions and a feasible one to implement. Any more?
One. Thank you. Next one, Daniel Diniz from UFBA, USP, turning of the cooperative distributed model predictive controller.
Good evening, everyone. I'm here to present the work, tuning of a cooperative distributed model predictive controller towards stability and performance. The work that is a work in process, in fact, is one of the projects of my doctorate, and with the orientation of Professor Márcio Martins and Daci Odiloac. Márcio is from Federal University of Bahia, and Daci is from USP. Well, this is a brief summary of my presentation. Here we have a brief introduction of the theme, some objectives, a case study, and some concluding remarks. Well, talking about cooperative distributed controller, what we have here is that we have a certain number of agents, here represented as infinite horizon multi-predictive controllers, that are controlling some subsystems of a major system. They are presented here with the same color because they share the same objective function. The difference between them is actually the decision variables. Each one has a certain subset of decision variables, what reduce the size of the problem that each one are solving, what makes them faster than possibly a centralized controller. However, they exchange information with a distributed suboptimal optimization algorithm that can be terminated at any iteration time. So the formulation of each agent in this controller, in this proposition, is actually an infinite horizon multi-predictive controller with terminal constraints, which are not here represented because they were already substituted directly into the optimization problem. Then the main idea is that each output variable should track what we call the artificial state, and this artificial state at the state is actually the set point that it might be tracking. The advantage of this strategy is that by not posing hard constraints, these controllers always find a solution at any time step. So this is an advantage, and the features are feasibility. Given any solution, it remains feasible at successive time steps. It converges to the centralized solution if enough time is given for the suboptimal algorithm. And optimality. If this algorithm is terminated at a certain iteration, let's say P, it will converge to a Pareto optimum. And the stability of the formulations, that's the closed loop to remain stable, it means that each agent follows the cost function of each agent is a Lyapunov function in the nominal case. But optimality and stability depends on defining minimal values for the elements of the suppression matrix. If this property is satisfied, the controllers are stable. So, how to tune this algorithm? Because we need to track both performance and stability. So we went to find, here the spacing model applied is the one that recovers the analytical step response of the system that was proposed by Professor Deloitte back in 2004. Here, in this model, we used because it's straightforward to segregate the subsystems. So the objective is to define a tuning algorithm that can track both performance and stability. So, to achieve the stability of the algorithm, we went back to the theorem, and we define, given a certain solution of this suboptimal algorithm that was terminated in a certain iteration, P, let's say, and proposing an inherited solution for the next time step. However, since the optimization was terminated before convergence, we set this inherited solution proportional to the available information among the controllers, because they will not exchange information to the next time step. That is a hypothesis that we set. So we need to, we set the inherited solution proportional to the available information. Then, evaluating the difference between the cost function at the iteration P and the cost function using the inherited solution, we find this. What's the characteristics? The suppression matrix only is related to quadratic terms. And the other terms that are not necessarily quadratic only depends on matrix Q, S, states, and etc. So given a certain scenario to define the states evolution and this matrix, gamma, if we set the matrix R higher enough, this cost function, this difference will be positive. Then we can use this as a restriction of offline tuning algorithm. So we define a tuning algorithm to perform, to track the difference between a set and closed simulation and the set point, penalizing variations of the input variables, and it needs to satisfy this restriction, this constraint, sorry, this constraint. That's the stability constraint that we imposed. So, in offline systems, we simulate a closed loop with certain matrix given by the auto tuning optimization algorithm. This will find the best trade-off between performance and stability. Then, to highlight the features of these controllers, we used two CSTR in series with a flash tank with a recycle stream that was used back in 2010 by Stewart. We choose two subsystems to work. It's the CSTR reactors and the flash tank. And to impose a harsh scenario for the controllers, the control horizon of both controllers as one to reduce the amount of information exchange between the controllers, and the maximum iterations of the optimization, the distributed optimization to one, to be very fast to solve as well. Since we are using a tracking problem, not a zoning approach, and this problem is not square, we set the composition of the accretant A to be in open loop for this example, and we want to control the compositions of the product B. That's why we set this matrix as high as possible, and we want to track the temperature as well, but with lower weight. So these are the results. The values found were not impeditive for the application. Let's compare it here. Here we have the composition of the product that tracks the set point, the composition of the temperature that can track the set point, and the cost functions of both agents are a Lyapunov function, monotonically decreasing. Here we have the absolute values and the first time derivative of this function to prove that it not increase. The only increase you have find here is on the change of the set point. So, some concluding remarks. We propose a tuning algorithm that can calculate the trade-off between stability and performance for this approach, and we successfully applied in a simulated scenario use this system provided in the literature. So we would like to thank to CAPS and the Ministry of Science, Technology, Innovation and Communication for the financial support. Thank you.
Thank you, Daniel. We have time for some questions.
Hi. I was just wondering, how did you calculate the derivative of the Lyapunov functional discrete? The discrete functional varying with time continuously.
It was actually pretty much straightforward, since we calculated, we know that this variable, that is the cost function, we calculated using the first time algorithm, the deviation between this number and the time.
More questions? I have one question. And can you explain why have you some zeros in your tuning matrix?
Oh, yes.
Is slide 12.
Yes. Since we here defined not to control the compositions of A, so when I showed here, it does not include this variable. This one, and this one, this and this one are related to the compositions of A that are set to be in open loop.
Okay.
Okay?
The idea is to reach a square system.
Yes, because we use it as a square approach. The main idea is to evolve this solution to the zone case, or the fat point approach.
Okay. More questions? Let's thank the presenter again. Now I'd like to invite Mauro Antonio Ravagnani to present the working title, Improving Energy Recovery by Optimal Control in Heat Exchangers Networks Under Fouling. He's from Estadual de Maringá.
Good afternoon. First of all, I would like to say that this work is developed by Carolina Carvalho under my supervision and with the collaboration of Professor Carvalho from the Department of Mathematics from the State University of Maringá. This work has started 2 years ago, and now is stopped because Carolina is in USA doing a PhD sandwich, and she is coming back very soon, and we will restart the project next semester. And our main objective is to study how to improve energy recovery in heat exchanger networks, trying to propose an optimal control in heat exchanger networks, but focusing on fouling mechanism. Fouling affects almost every industrial process, especially heat exchanger networks. We are talking now about shell and tube heat exchangers, but it can be expanded to all kinds of heat exchangers. What is fouling? Fouling is an unwanted material deposition on heat transfer surfaces. So we expected that fouling can exist, but we don't want it. Fouling is a dynamic process, so gradually we have a degradation of the thermal performance of the heat exchangers. So it's necessary to study these mechanisms. Some authors use the term fouling resistance, but originally the first works treat the problem as a fouling factor, a number that is an indicator of the amount of solid material deposited on the heat transfer surface. But we know that it's not the correct way to treat the problem, because the first model was proposed in 1959 by Kern and Seaton, and they considered the mechanism as a difference between the deposition and the removal of material during the time. So we have a fluid flowing inside a tube, for example, and we have a deposit layer in the surface area. So this proposition, it was the first one, and maybe the first work was not able to predict effectively how it works. And of course, it has some problems, but it is possible to consider 4 different falling behaviors over time. The first one is a linear rate, where the difference between phi d and phi r is constant. The second one is a descendant or a falling rate, where phi d is inversely proportional to the deposit thickness layer. We have a asymptotic rate, where phi d remains constant and phi r is inversely proportional to the deposit thickness layer. And we have the most complicated case. We know it sawtooth rate, and it depends on the variation on operational conditions in the heat exchangers. But the problem is that this model obviously has some deficiencies. One of them is it does not include chemical reactions and some mass transfer process in the base most falling process. It's known that most common falling mechanisms are crystallization, particulated, biological corrosion, and chemical reaction falling. So this original method doesn't consider these features. And we know that the falling resistance can be estimated as a function of some physical properties, density, for example, velocity and temperature of the fluid, its oxygen content, the hydraulic diameter of the fluid where the fluid is flowing, the surface temperature, and the time of use of the equipment. So the main issues with conventional models to predict the behavior of falling is we need a good parameter estimation, reliable data source, robust optimization methods, and we may consider or not consider how important variables that affect falling. Well, in this project, we intended to redirect the falling behavior by using artificial neural networks that are intelligent paradigms that try to model some phenomenon by simulating the process of learning of we human beings. If we have an artificial neural network well trained with an adequate number of data and using a suitable learning algorithm, it's possible we can provide acceptable results for relating the dependence and independent variables, even for nonlinear and very complex process systems. The main advantages of artificial neural networks is that they can learn by examples. They are simple and powerful models, and there exist well-developed algorithms for training it. The idea is use a structure for this artificial neural network with 2 layers, a hidden layer and an output layer, with the inputs, a sigmoid function in the hidden layer, and a linear transfer function in the output layer. U is a vector of inputs. We can consider the physical properties, density, temperature, velocity, time of operation. Y is the system output. In our case, the fouling resistance. E, we have the weight matrix and the bias for the layer. We used the Levenberg-Marquardt algorithm for training the network, and it was trained offline. This algorithm is an iterative technique that locates the minimum of a cost function. We solve an optimization problem as the sum of squares of this linear function. So we use MPC model predictive control to try to control the heat exchanger network. And the MPC use a model of the system to make predictions. And now we have a problem because the MPC depends on the process model. And if we have a very good model, we don't have too much problem. But if we don't have a very good model, we can have problems. In our case, we use I will show a lumped model for the heat exchanger. The MPC solves an online optimization problem, and the artificial neural network fouling method is incorporated in the system model, and the MPC can also handle some constraints in the input and output variables. Here is the cost function. We have the schema of the MPC and a block diagram of the process. A flow chart of the MPC and the artificial neural network fouling rate model. We have the fouling data, the training of the artificial neural network to predict the fouling resistance. We update the heat exchanger network model considering this fouling resistance, and we apply the MPC control to control the outlet temperature by adjusting a flow rate, and we can minimize the utilities requirement. Our case study, we have a heat exchanger with 4 devices, one cold stream and 2 hot streams. Our main objective is to control the temperature of the H1 stream by manipulating the flow rate of C1 stream. So we have as manipulated variable C1 flow rate and as controlled variable H1 outlet temperature. We use a lumped model for each heat exchangers because if we use a distributed model, we will have a partial differential equation system. So it's a manner that we used to solve the problem originally, but we will try to improve this in the future. The heat exchanger coefficients of each heat exchanger is updated by the artificial neural network model. And our simulations was provided in MATLAB, and these are the equations of the system, the ordinary differential equation. This is the training and the validation of the neural artificial network. We can see that it was not so good training and worst validation, but it works. We used the Levenberg-Marquardt algorithm, and with a mean squared error very small. And as a result, we tested 4 different situations, 6 months, 12 months, 18 months, and 24 months. And we applied a step change of 5% in the flow rate of C1. And in our conditions simulated, the set point considered was 248 degrees Celsius. And this is the behavior of the closed loop. And if we didn't have any control, we will we will have these utility demands. As we can see, as the time passes, we will have more and more utilities to maintain the original heat transfer as designed. As conclusions and future work, we would like to say that the artificial neural network models can be an efficient tool to predict falling rates considering several input variables that affect directly the falling resistance, and the combination of the artificial neural network falling model with the MPC for the heat exchanger network control can lead to energy saves by minimization of the usage of utilities. Simulations that consider different disturbances need to be performed, and a bigger set of falling data would be necessary to extend the range of operation in which the artificial neural network to be valid. And networks with more complex dynamics would be also interesting to be simulated with more heat exchangers, with different kinds of heat exchangers, like not only shell and tube heat exchangers, but another ones. And some reference, and I would like to thank you your attention, and if you have any questions, I'm available.
Thank you. We have time for one just quick question. The question can be answered in Portuguese, no problem. So I have one question.
Okay.
And what do you think that your neural network has reached R square quite low during the training and validation procedure?
We have problems with the data. We need a bigger set of data, and maybe this is the big problem. I think if we have 10,000 more times the data, we can adjust the problems.
Thank you. Let's thank the presenter again.
Thank you very much.
Now I would like to invite Pedro Henrique Veiga Rezende from UniFe to present work entitled Variability Analysis for Fault-Tolerant Control in Chemical Processes.
Boa tarde, meu nome é Pedro, eu sou estudante de graduação de Engenharia Química lá na Universidade Federal de Itajubá. E o que eu trouxe aqui é o meu estudo de iniciação científica que eu fiz com o professor Tiago Costa, que a gente faz sobre a análise de operabilidade na aplicação de um controle tolerante em processos químicos. Bom, aqui está o escopo da minha apresentação. Só dar uma contextualizada, né, falar da motivação para o estudo e dos objetivos. Falar também do pouco da metodologia, né, do caso, o controle tolerante a falhas que a gente aplicou, que é um estudo do meu orientador, né, lá da tese de doutorado dele, que ele pegou o atuador virtual e propôs a extensão da aplicação do atuador virtual com um horizonte móvel em tempo discreto, para utilizar daquelas ferramentas do controle preditivo, como foi apresentado aqui foi abordado aqui nas apresentações anteriores, aquelas ferramentas lá do MPC, de equação de otimização, etc. Os resultados, então, eu trouxe um estudo de caso dentre os que eu fiz lá, para poder exemplificar, e, por fim, a conclusão. A introdução aqui é a motivação do nosso estudo. A gente partiu, então, o motivo seria a dependência dos processos químicos, a alta dependência de uma estrutura de controle, né? Ainda mais porque, agora, com a crescente automação, o sistema fica cada vez mais vulnerável a uma falha, né? Uma falha que atinge lá um atuador ou um sensor da malha de controle. Isso pode afetar a performance do sistema e também causar uma parada repentina na planta, então até mesmo trazer risco de segurança lá para o operador, para o processo. Sendo assim, então, a aplicação do controle tolerante a falhas, ela se faz necessária, e para isso, para poder tornar o sistema estável, né, até que ocorra a troca ali do equipamento defeituoso. E, para isso, é de interesse determinar as restrições relacionadas às variáveis controladas do processo. Porque, num cenário de falha, a planta tende a violar essas restrições, que pode trazer o risco à segurança, né? E aqui também a gente usa ela na implementação da estratégia de controle. Então, aqui são os objetivos do meu trabalho, da minha iniciação. A gente fez uma simulação de faltas num sistema simples, de falhas. Em seguida, a gente implementou, então, a análise de operabilidade, que eu vou mostrar algumas definições aqui, lá do trabalho do artigo do professor Lima, e a gente aplicou elas no contexto de falhas, para sistemas que têm falhas em um de seus atuadores. E, em seguida, então, a implementação do controle tolerante a falhas, que foi lá o estudo do meu orientador, baseado num horizonte móvel. Bom, então, um pouco da metodologia, né? Aqui eu trouxe a estrutura básica do controle tolerante a falhas, né, onde ele faz a reconfiguração do controlador em tempo real, diferente do controle tolerante passivo, que tem lá as dinâmicas de falha já embutidas no sistema, na concepção do controlador. Esse aí faz a reconfiguração em tempo real, que pode ser através do monitoramento da planta e pode ser feito também em referência a um modelo da planta no estado nominal. Então, calculando ali o desvio, ele pode alterar, então, a lei de controle para adequar aos objetivos do controle que você está fazendo da planta. Aqui é a representação do atuador virtual, onde eu considero as falhas em um dos atuadores da planta. O meu trabalho não aborda a parte de detecção da falha, a gente só assume que tem uma falha em um dos atuadores. E aqui dá para ver que o bloco de reconfiguração ele faz, então, a reconstrução do sinal que é enviado pelo controlador nominal. Ele realoca esse sinal para os atuadores remanescentes. Por caso de você não ter uma redundância física no seu sistema, os outros atuadores eles vão ter que dar conta dessa falha que ocorreu. Então, ele realoca, considera lá os limites dos atuadores remanescentes, e o controle das variáveis passa a ser feito naquelas faixas, como foi demonstrado aqui na apresentação anterior, do professor Jorge. Tem também a parte de ocultação da falha, para o controle nominal, para ele não ficar tomando ações indevidas, que acontece aqui do YP para o YC. E o interessante também é notar que a reconfiguração ali não afeta a estrutura do controle nominal, né? Bom, aqui então algumas das definições que são aplicadas para o atuador virtual de horizonte móvel, lá na equação do problema de otimização. Aqui tem um modelo, então, espaço de estados da planta, no comportamento nominal, o comportamento em falhas, o desvio do sistema, que é esse x-delta aí, que vai ser o que a gente quer minimizar na equação de otimização, e aqui a parte de ocultamento da falha, que eu expliquei no slide anterior. Aqui são alguns intervalos que são necessários definir para fazer a análise de operabilidade lá da planta. São 4 intervalos, esse tem aí 2, então, que são as entradas, né, as entradas disponíveis para o sistema, considera os limites físicos associados aos atuadores, e as perturbações esperadas para o sistema, o que é diria uma restrição aqui uma restrição não, mas uma limitação do meu estudo aqui, que deveria considerar a falha, o valor dessa falha, preciso saber quais são os valores que elas tomam na execução do processo. O intervalo, então, de saídas desejável, que seriam as limitações que você quer impor às saídas controladas com relação ao objetivo seu de controle. E aí, por fim, o intervalo de saídas disponíveis, que considera, então, os 2 intervalos lá, o de entradas disponíveis e o de perturbações esperadas, para calcular as saídas, então, as saídas disponíveis para o sistema. Isso aí é feito para o processo em malha aberta, sem implementação do controle, considerando as matrizes de ganhos associadas ao estado estacionário do sistema. Aqui a equação do problema de otimização do atuador virtual com horizonte móvel. As variáveis de decisão ali, então, são as variáveis de entrada da planta em falha. E aí a gente quer minimizar, então, esses 3 termos. Aqui associado ao desvio em relação ao estado nominal. Esse segundo termo aqui leva em conta a ação de controle, para fazer esse desvio ser o mínimo possível. E ali associado às folgas que a gente adicionou às restrições aqui. Essas restrições aqui determinadas pelo intervalo de operabilidade. Bom, aqui os resultados. Então, a gente pegou um sistema de 2 CSTRs, que é um sistema bastante recorrente aí na literatura, como foi mostrado também na última apresentação que teve, na anterior a essa, aliás. E aí a gente quer fazer o controle das temperaturas dos tanques usando a vazão de resfriamento nas 2 jaquetas. Aqui está o modelo não linear para o processo do primeiro e do segundo tanque. E aqui, então, o modelo do sistema com base naquelas matrizes de ganho. A gente considerou, então, o controle das temperaturas 1 e 2 dos tanques, com base nas vazões das jaquetas. Aqui. E considerando as temperaturas, as variações na temperatura da água de resfriamento como possíveis fontes de perturbação para o nosso sistema. Aí, então, a gente definiu os nossos intervalos com base no que a gente estipulou, que as vazões das jaquetas, os limites dos atuadores seriam de menos 0,02 a 0,02, valores aqui para as perturbações. E aí a gente considera um cenário de falha na válvula de alimentação da jaqueta do reator 1. Aqui não está representado, mas tem uma corrente de reciclo da saída do segundo reator para a entrada do primeiro, para que dessa forma o controle da temperatura do primeiro reator possa ser feito. Aí aqui, como por se tratar de um sistema de 2 variáveis, a gente consegue plotar, então, o intervalo de saídas desejáveis. Essa análise aqui de operabilidade é feita para sistemas não lineares, não quadrados, com número de entradas menor que o de saídas, que é o que acontece quando ocorre uma das falhas nos atuadores do sistema. Então, aqui o DOS. Aqui o AOS para o caso servo, considerando as perturbações iguais a 0. Aqui, esse plano em laranja ele é o conjunto de todos os AOS para todos os valores de perturbação estipulados. E aí, por fim, o intervalo de saídas disponíveis para o sistema, que a gente considera, aqui a gente fez em mesma proporção do DOS, do desejável, mas não precisa ser. e a gente pega ali, as extremidades dele estão associadas aos limites máximo e mínimo das saídas disponíveis, com base nos valores de perturbação. E aí a gente obteve, então, essas restrições aí, as máximas restrições possíveis para as temperaturas dos tanques. E aí a gente considerou, então, 2 cenários de perturbações, em que as perturbações estão constantes nesses valores. Aqui, então, o comportamento nominal do sistema, para a perturbação de TCW-I1, que é a temperatura da água de entrada na camisa de resfriamento do tanque 1, igual a 5 Kelvin. Aqui é para o processo em falha, você vê ali em azul a resposta do sistema, você vê que aqui o atuador travado, uma coisa que eu esqueci de mencionar, a falha considera de travamento no estado estacionário, né? É o tipo da falha que a gente considera. Então, QCW travado no estado estacionário, o controle nominal não consegue fazer trazer de volta para o set point a temperatura do tanque 1. E aqui a aplicação, então, da reconfiguração. E ali, então, intrasejado, ali estão as restrições que a gente determinou, tanto para o tanque 1 quanto para o tanque 2. E aqui uma representação da dinâmica do processo, aqui num plano de fases aqui de T1 e T2, para onde ela foi ali dentro do intervalo que a gente considerou de máximas restrições aplicáveis. Aqui para o segundo caso, então, comportamento nominal, a falha, agora num valor limite da perturbação de 10 para a temperatura da água do tanque 1, da jaqueta de resfriamento. Aqui é para onde ela é levada, ali para fora do intervalo onde a gente estipulou. E aí aqui a aplicação da reconfiguração, você vê que ela atinge o limite mesmo da entrada, ali, o valor limite, para poder trazer o sistema para o ponto ali de restrições máximas. Bom, as conclusões, então, do meu trabalho, como é um estudo inicial, ele está cheio de considerações e restrições, mas os resultados que a gente obteve indicam que a aplicação da análise de operabilidade ela é viável, pode ser aplicada na determinação dessas restrições, com base no que a gente viu. Mas isso foi para as considerações que a gente fez no estudo, né? Então, como trabalho futuro, a gente é de interesse desenvolver essa técnica aí para aplicação industrial mesmo, em problemas industriais reais. E para isso a gente precisa estender a metodologia então para sistemas de dimensionalidade maior, além dessas de duas dimensões aí, como eu apresentei, e considerar outros tipos de falhas em atuadores que não seja só o travamento, ainda mais no estado estacionário, e comportamentos diferentes das perturbações. E aqui os agradecimentos. É isso, obrigado.
Many thanks, Pedro. Questions? No questions? All right. Thank you. We'll finish the session.
Okay. Now we'll have the break for the coffee break, a real coffee break with something else than coffee. And it will be in another place, a different place. Is about 6-7 minutes from here walking. The map is in the homepage of the conference, in the poster section. There is a map but there is also the people from the support committee that's outside to take all of you to the poster section. And there will be the coffee break. So if you want the coffee break, you have to find the path and go there. Okay? So see you there now. We will start the coffee break.
Bem, eu estou aqui no jardim da minha casa, aqui no refúgio em Teresópolis, e fui convidado para colaborar nesse primeiro encontro de engenharia de sistemas em processos, feito no Brasil, né? Uma coisa que eu achei brilhante, que foi que resolveu algo que me angustiava demais há muito tempo, era como traduzir o Process System Engineering. A colocação dessa preposição em processos ficou absolutamente brilhante. Engenharia de sistemas em processos. Eu achei que quem bolou isso deve ser parabenizado, porque ficou perfeito. Então, esse encontro me deixou impressionado, que são 44 trabalhos orais e 215 trabalhos apresentados em forma de pôster. Quer dizer, isso mostra bem a produção da área no Brasil, e nada mais correto do que chamar esse prêmio que o professor da Silva está recebendo, do prêmio do professor Carlos Augusto Guimarães Perningeiro, que foi realmente o pioneiro na área.